Ever wondered how databases are designed? Well, it's an intricate process that requires careful planning and execution. Database design is all about creating a structure that meets the needs of an organization or application. This isn't just a one-step process, but involves a systematic approach, from understanding the requirements to maintaining the final product. First, we begin with requirements analysis, where we gather and analyze the needs for the database. Then we move on to the conceptual design, creating a high-level structure of the database that is independent of any specific database management system. After that comes the logical design, translating the conceptual model into a logical schema. And then we're on to the physical design phase, converting the logical schema into a physical database implementation. Finally, we implement the database, test it, and evaluate its performance. And of course, there's ongoing maintenance and evolution because just like any other technology, databases need to evolve over time. So let's delve into the first step of the process, which is requirements analysis. The foundation of any successful database design is a thorough understanding of the requirements. Now you might ask, what does this entail? It's all about delving into the nitty-gritty of business processes, pinpointing stakeholders, and defining the data needs and objectives. Imagine you're a detective, sifting through clues to solve a case. Here, your case is to create a database that fits its intended purpose, like a glove. It's not just about what data you'll store, but also how the data flows, interacts, and transforms within your organization or application. It's about capturing the essence of your data ecosystem. This process, often referred to as requirements analysis, is crucial. It sets the stage for everything that follows. It's like sketching a blueprint before constructing a building. With the requirements clearly defined, we can move to the conceptual design phase. This is where the magic begins, translating your requirements into a model that forms the skeleton of your database. But let's save that for the next scene. Conceptual design is where we begin to give shape to our database. Now, let's dive into the process of conceptual design. At this point, we're looking at a broad overview, a bird's eye view, if you will, of the data that will be housed within our database. We're not concerned with the nitty-gritty details just yet. This is all about sketching the big picture. To create this initial roadmap, we use a technique called entity relationship, or ER, modeling. This isn't as daunting as it sounds. It's just a way to visually represent the data and the relationships between different elements of that data. Let's break it down. An entity is essentially a thing or an object. It could be a person, a place, a product, or anything else that we want to keep track of in our database. For instance, if we were designing a database for a bookstore, our entities might be books, authors, and customers. Each entity has attributes, which are specific pieces of information that describe it. For our book entity, attributes might include the title, the publication date, or the genre. For the author entity, we might have attributes like the author's name or their birth date. Then we have relationships. These are the connections between our entities. For example, an author writes a book. That's a relationship. A customer buys a book. That's another relationship. Through ER modeling, we're able to visualize and understand the complexity of our data. We see what data we have, how it's related, and what it represents. Once we've identified our entities, defined their attributes, and established the relationships between them, we've got our conceptual data model. It's a high-level blueprint of our database that outlines the core structure, independent of any specific database management system or implementation details. Remember, the focus here is on what the data is, not how it's stored or manipulated. We're laying the foundation, setting the stage for the more technical aspects of database design that will come next. Once the conceptual design is complete, we can start translating it into a logical schema. Logical design is where we start getting technical. As we delve into the realm of logical design, we're essentially translating our conceptual data model into a logical schema. This is a pivotal step, as it's here that our high-level concepts start to take on a more concrete form that can be implemented in a specific database management system, or DBMS for short. So what does this translation involve? Well, it's about defining tables, columns, and keys, and establishing relationships between these tables. Let's break it down a bit. For every entity in our conceptual model, we create a table in the logical schema. Each attribute of these entities then becomes a column in the respective table. As for the keys, they play a crucial role in maintaining the integrity of our data. Primary keys uniquely identify each record in a table, while foreign keys establish relationships between tables, linking records based on shared attributes. This is also the stage where we consider the rules of normalization. These rules help us ensure that our database is free from redundancy and that it's structured in a way that avoids potential anomalies. For example, it's here that we strive to achieve the third normal form, or 3NF, which ensures that every non-key column is functionally dependent on the primary key. In simpler terms, each piece of data in a table should relate directly to the unique identifier of that table and nothing else. Normalization doesn't end with 3NF though. For more complex databases, we may also consider Boyce-Codd normal form, or BCNF, which adds further restrictions to ensure every determinant is a candidate key. As we wrap up the logical design, we're left with a schema that clearly outlines how our data will be organized within the DBMs. It's a vital blueprint that guides us further into the more tangible realms of physical design and implementation. Now that we have a logical schema, it's time to consider the physical aspects of our database. Physical design is all about performance and storage efficiency. This is the stage where the logical schema, which we carefully crafted in the previous stages, is transformed into a physical database implementation. It's like going from blueprints to constructing a building, brick by brick. The logical schema is the blueprint, but the physical design is where we decide on the materials and construction techniques. We're looking at how to store the data, how to retrieve it, and how to manage it efficiently. This phase is about making decisions that will greatly affect the performance of the database and the applications that will use it. One of the first things we have to consider is how we're going to structure our storage. We need to think about the type of storage devices we will use, how they are connected, and how we will organize data on them. This involves considering factors like data access patterns, response time requirements, and the amount of data we expect to handle. Next, we need to consider indexing strategies. Indexes are like the contents page of a book, helping us quickly locate data without having to scan the entire database. Deciding what to index and how can have a significant impact on the speed of our data retrieval. Partitioning is another important aspect of physical design. This involves dividing our data into smaller, more manageable pieces, which can be stored and accessed independently. It's a strategy that can help improve performance, especially in large databases. Once we have these decisions made, we move on to the implementation phase. Here we're creating tables, defining constraints, indexes, and other database objects. We're also loading our initial data into the database. It's like moving furniture into our newly built house. In this phase, we use specific tools and utilities provided by the database management system to implement the database schema and configure performance-related settings. Everything we've planned and designed now comes to life. With our database implemented, we need to ensure it works as expected. But that's a story for the next scene. For now, let's take a moment to appreciate the complexity and elegance of database design and implementation. Testing and evaluation are critical for ensuring the quality and performance of our database. Once we've built our database, it's time to put it through its paces. This is where we validate its integrity, verify the accuracy of our queries and transactions, and assess its performance. Let's begin with data integrity validation. This process ensures that the data in our database is accurate, consistent, and reliable. We're essentially checking that our database is doing what it's supposed to do, holding the data it's supposed to hold, and that there are no errors or inconsistencies that would compromise its utility. Next, we verify the accuracy of queries and transactions. This involves running a series of tests to ensure that our database is returning the correct data when queried. We also check that transactions, such as updates or deletions, are being executed correctly. This is a vital step, as the accuracy of data retrieval and modification directly impacts the usefulness of our database. Performance assessment is another key aspect of testing. Here, we're looking at how well our database performs under various conditions. We might test how it handles high volumes of data or how quickly it processes complex queries. We're essentially stress testing our database to ensure it can handle the demands that will be placed on it. We shouldn't forget about user acceptance testing either. This is where we gather feedback from the end users of our database. Their input can provide valuable insights and help us make necessary adjustments to improve user experience. But our job isn't done once the database passes all these tests. The final stage in our database design methodology is maintenance and evolution. This is an ongoing process where we monitor performance, optimize queries, apply patches and updates, and make modifications to the schema as needed. This ensures that our database remains robust, efficient, and effective, even as requirements or technology change. And that's a wrap on our journey through database design methodology. Remember, each stage plays a crucial role in creating a robust, efficient, and effective database.